Hello and welcome to part 6 of Module 17 in our C language series. In today's session, we're going to focus on binary trees. So one may ask, what is special about binary trees? Well, binary trees allow us to do rapid searching, rapid insertion, as well as rapid deletion of data items. How is this possible, you may ask? Well, that's because binary trees use the divide and conquer approach that we discussed when we spoke about a binary search. And if you want to refresh your memory on that discussion, the link to that module is in the description below. Now, what does a binary tree consist of? Just like a tree, the binary tree consists of nodes, which in technical terms are data items. Right? Each item in the tree would consist of information along with a link or a pointer to a left node and a link or a pointer to the right node. Okay, so each item in the tree is called a node, as I said earlier, but is also referred to as a leaf. The first node or the topmost node is called the root node. Any node that does not have any subtree or any other node attached to it is called a terminal node. And if this is not clear to you, it should be clear now when we look at a sample binary tree. And so we have a node here, and you can see there are two pointers, each pointing to a left node and a right node. And these nodes in turn can have their own pointers. You can see the one on the left has two, the one on the right has just one, right? And these will point to, again, for the left node, a left and a right node, but the one on the right points to just one node. It is not necessary that just because we have this node pointing to 2, that this one needs to point to 2 as well. Right? This is still a binary tree. Right? The top node or the first node is the root node, and the nodes on the left of the root are called the left subtree. The nodes on the right of the root are referred to as the right subtree. The nodes at the bottom of your screen that do not point to any other nodes, these three that is, these are referred to as the terminal nodes, right? And you could have a situation where you just have a root and no other node, and then the root would be the terminal node. Now, how do we code using the binary tree concept? And then most functions associated with binary trees would be recursive. Why? Because every subtree within the binary tree could be another binary tree, right? And would be treated as such. How do we then access each node in the tree? And this is what is referred to as tree traversal, right? Now let's talk about traversing the tree. There are three ways we can do this. Let's look at those. So we have a tree here, binary tree that is, with the different nodes, right? And of course we have the root, the left subtree, the right subtree, and the terminal nodes, right? Now we could traverse this tree using the in-order approach, which means that we access the left subtree first, that's A, B, C, then the root, D, and then the right subtree, E, F, and G. We could also traverse the tree using the pre-order approach, which is the root first, then the left subtree, and the right subtree. Or we could traverse the tree using the post-order approach, which is the left subtree first, then the right subtree, and finally the root. Now, just to give you a recap on how we would write code to traverse the tree using any of these approaches, or in order, we would visit the left subtree, the root, and then the right subtree. For pre-order, we would visit the root, the left subtree, and then the right subtree. For post-order, we would visit the left subtree first, then the right subtree, and finally the root. Now, keeping all this in mind, let's write some code. Write code to build a sorted binary tree print the value stored in each node by traversing the tree first in order, pre-order, and post-order. How many functions would we need? Well, we would have 3 different functions for these different approaches. So we would have an in-order function, a pre-order function, a post-order function. And then, of course, we would have main, and we would have a function to build the tree. Let's now go to code blocks and we can start a new file. And we start with hashtag include stdio.h and then hashtag include stdlib.h. Struct, which is our structure tree, and that's going to have just char info, just that one character, no strings or anything else, and then the pointers. So struct tree star left to point to the left node, and struct tree star right to point to the right node. And that's all for the structure of the tree. And now we have our variables, global variables, struct tree star rt and struct tree star root. Okay. Functions that we will have: struct tree star make tree. This is going to be the function that will build a tree, and it's going to return a pointer to the structure of tree type. Okay, so it's going to take parameter struct tree star root, struct tree star rt, and then char alphabet. You can call that whatever you like. That's just the character that the user has entered that's going to be passed in. Okay. Then we have void in order. So this is going to be the function that is going to traverse the tree in order, and it's just going to take in the root as argument. So struct tree star rt. Okay, rt essentially will be initialized to root, as you will see shortly. Then we have void pre-order, going to traverse the tree in a pre-order manner, right? So again, it's going to take just struct tree star rt as parameter. And we have one more, which is post order, right? So covering all the ways we can traverse the tree, struct tree star rt. Okay, we have one more function which I'll come to after we have executed the code, showing us the different ways to traverse the tree. So you can comment this function out. Like I said, I'll come to it later. Just put it in now, so we are declaring it, and that's called print b tree. That's going to take struct tree star rt and an integer as parameters. Right? Now our main function, and within main, first of all, root will be initialized to null. Char input letter, which is going to be used to get input from the user. We have an infinite loop. You can use a for or a while for this purpose. You can initialize rt or assign to rt the value of root. Root, remember, is going to be the root node. Yeah, so we're initializing rt to root and then passing that as argument, of course, along with root to the make tree function, right? So printf, enter any letter, and then scanf %c, comma, that's going to be ampersand input letter, right? And then of course f flash stdin, right? Then we check if input letter, right, is equal to /n, which means the user pressed the enter key, which in turn means the user does not want to enter any more letters. So we'll break out of this infinite loop. Right? Otherwise, we check if not root. Okay, which means that there is no node in our tree. Our tree is essentially empty, and we'll assign to root now the return value of make tree. And make tree is going to take as argument root rt, which will both be null in the first instance, comma, input letter, right? Else, which means that we already have a root, we just call make tree because we don't need to have our root node created, right? So just pass in root rt and input letter. Hope you're with me so far. Now, out of this loop, we'll have a printf statement just saying traversing the tree using in order approach. That's just for your reference actually, right? So that we know what the program is doing. And then we call the function in order, passing in root as argument. Then you can print a /n before using another printf statement to indicate that we are now traversing using pre-order. And then call the function, that's pre-order, passing in root. Again, printf /n. Right, and finally a printf statement saying we are traversing using post order. Call the function post order, passing in root. And then exit. Right, so this exits the program. So that completes the code for our main function. So now let's write the code for the make tree function. So struct tree star make tree, and that's going to bring in parameters struct tree star root, struct tree star rt, and char alphabet. Right, within this function we first check if rt is null, right? So here we say if not rt, then first of all assign memory to rt. So rt equal to struct tree star, and then of course malloc size of struct tree, right? And then we check if malloc returned a null. So if not rt, then printf out of memory and exit 1. If malloc has not returned a null, then we can now assign to rt info the value the user entered, that's alphabet. Okay, so this is essentially a new node that we have, and rt left should then point to null, which is important, right? And rt right should also point to null. And then we can check now if not root, which means we do not have a root node, then we return rt as a root node. Okay, Otherwise, we check if alphabet is less than root info, right? Then root left equal to RT. Otherwise, root right equal to RT. Okay. And then, of course, return RT. Okay. Now, if RT is not a null, then what we do is we check if alphabet is less than RT info, right? Because RT is not a null, so we're checking against RT info. If it is less, we recursively call make tree with RT now as root. Okay, remember every subtree can be treated as a binary tree, right? And then RT left and alphabet. Otherwise, we call make tree with RT using RT right now and alphabet. Okay, and that completes our make tree function, right? Now we'll write the code for in order. So void in order, and that's going to take or bring in struct tree RT. And here we'll check first if not RT, which means if RT is null, then return. Otherwise, we'll recursively call in order, passing in RT left. Remember how the in order approach works, right? First, we visit the left subtree, so that's what we are doing. Now we visit the root. So what we're going to do is we're going to print the information. So printf %c, RT arrow info. Right, so what will happen here is, remember, we are using recursion. So this function is going to call itself until RT returns a null, right? And after that, it will move to this printf statement, correct? After each printf, we want to print some spaces. Just 3 or 4 will do, so that we have a space between the printing of each node, right? And then we'll call in order recursively again using RT right as argument. Right, if you're not clear on how recursion works, then I suggest you go back to the module where we discussed recursion. You'll find the link to that module in the description below. This completes the code for in order. We now write the code for pre-order, right? So void pre-order, and again the parameter coming in is struct pre *RT. Okay. Within this function, we check if not RT, then return. Otherwise, we need to print first, right? Because remember, we are visiting the root, then the left subtree, and then the right subtree. So printf %c, comma, RT info. Then we call pre-order recursively, passing in RT left as argument, right? So this will go on until RT is null, after which we call pre-order with argument rt right. Okay, that completes the code for pre-order. And finally, post-order, struct pre-rt, and again we check if not rt, then return. Otherwise, remember for post order, we printing or visiting the root last. So we'll base our printf statement also on that. So first we call post order, passing in rt left as argument. Again, this will go on until rt returns a null. And then we call post order using rt right as argument. And then printf basis 3 or 4 will do. And then printf %c, comma, rt arrow info. And that completes the code for all these functions, right? Essentially the program. So let's now run this code and see the results. Okay, we are missing a semicolon there. So let's enter some data now. Let's say D. Let's keep it at capital letters so it's easier to read. F, B, E, C, G, A. You can see now in orders A, B, C, D, E, F, G. Pre-order is the root first, then the left subtree. All these are less than the root, and then the right subtree. All these note are greater than root. Then post order, we have left subtree, right subtree, and then the root. Okay, so I hope that's clear. Now let's write the code for the print b-tree function that I spoke about earlier. Right, so you can put that code anywhere you like. I'm going to put it just after make tree. So here we say void, and that's going to be print b-tree, and that's going to bring in struct tree star root or rt and int I. Within this function, we have a count in as integer, and then we check if rt is null, then return. Otherwise, we call print b-tree recursively, passing in rt left as argument along with I plus 1. So every time this is called, I is going to be increased by 1. Okay. And then we have a for loop for count equal to 0, count less than I, count plus plus. Okay, and all this is going to do is printf some space. In effect, this function is printing the tree sideways, if you will, as you will see shortly. And printf %c \n, so we go to the next line, comma, rt arrow info. Okay, and then we call print b-tree again recursively, but this time we call it with rt right as argument along with I plus 1. Right? Now we've already declared this function, so we can uncomment this statement, and then we need to call this function from main. Right? So what we will do is we will not run these now, so you can comment this block of code out, leave the exit statement intact, and just after that bracket, which is the bracket for that while loop, right, you will put in a statement calling print b tree. So print b tree, and we'll call that using root and 0 for I, which is the integer. Okay. So now let's run this and let's enter some data. So D, F, B, E, C, G, A. So you see we have the left subtree, the root, and the right subtree. Okay, you can run this using different letters, right? So you enter, for example, G as root, and then let's say enter A, and then Z, and then F and R and E, and let's say Y and C and K. So now we have A, E, C, and F all for the left subtree, and Z, R, Y, and K for the right subtree. Press enter, and you get a different shape of tree, right? The root, then the left subtree, and the right subtree. So you can play around with this program, right? So I hope this is clear. This now finishes our session for today. In the next session, we'll talk about deletion of nodes in a tree, as well as searching for a particular value using a binary tree. So till then, take care, stay safe. Bye.